Okay, so let's continue our discussion about work. We initially defined work as being the product of force times the displacement of the object, and whenever we were identifying whether or not work was present, because we do have some situations where there's a force being applied, but no work is being done according to physics, we said that the force and the direction of the displacement have to be in the same plane. They have to be along the same axis. So we initially discussed a situation where we have a crate, just like this woman in the picture, that is being pulled so that the crate experiences some displacement because of the force applied. And so here we said that the work done was equal to the force times the displacement. Now the formula says times the cosine of theta, and so at that time we discussed how the angle in this case would be an angle of 0 degrees because the force is in the horizontal axis. It is perfectly to the right in this example. The displacement is also in the horizontal axis, perfectly to the right, and so the angle between these two vectors came out to be an angle of 0 degrees. There was no angle to be measured. They were exactly the same direction. So when we went to plug in our numbers, we said that the cosine of 0 actually gives us a value of 1. You can put that in your calculator right now and see that cosine of 0 is 1. So this means that the force that she applied times the displacement is just being multiplied by the number 1. What that should mean to us as far as interpreting the work that she's done, it means all of the force was being used to produce the work, and it means that she's created positive work because the force is in the same direction as the displacement. Now, if we were to look at the illustration that they have given us here, now they have taken our force, and instead of having it on an angle, instead of having it perfectly horizontally, they have put it on an angle. So I want to show you, let's say that she is pulling with 100 newtons of force, and this crate experiences a displacement of 5 meters. Now, if she is pulling on this crate with 100 newtons of force and creates a displacement of 5 meters, then she is going to perform 500 joules of work, right? If it's perfectly horizontally. But now if she takes her force and she puts it on an angle, she is no longer doing 500 joules of work. She's actually doing less than 500 joules of work. Now, the woman is still exerting 100 newtons of force onto the crate, but not all of that force is actually being used to perform work. Remember, if we were to focus on the vertical motion or the vertical component of her force here, the displacement of the crate is 5 meters, but 100 newtons is along this diagonal, and all diagonals can be broken up into horizontal and vertical components. So the vertical component that she is applying is actually going to essentially be wasted force because it's not going to be used to do any work to move the box horizontally. Let's just think about this. Her force is upward. The box is moving to the right. That force is doing nothing to work on that box, okay? It's not helping, contributing, affecting that horizontal work in any form or fashion. So let's just look at how the math tells us that, okay? So if we were to draw the force vector in real life is right here of 100 newtons. But we are considering the vertical component of that force. And so the slide here is telling you that the angle theta represents the angle between the displacement and the force. So let's look at this illustration. The displacement is right here along the horizontal axis. The force that we are analyzing in this case, the vertical component, is along this axis. Those two vectors are at a 90-degree right angle to each other. So when we are calculating the work done here, this is going to be the force times the cosine of theta, because it is the force component that is parallel to the direction of the object's displacement. Okay, so we're going to put in 100 newtons of force, but we have to turn around and multiply that by the cosine of theta, which in this case is the cosine of 90 degrees. So if you were to take your calculator and put in the cosine of 90, you would see that this comes out to be a value of 0. So we would essentially be multiplying 100 times 0 times 5, which means in the vertical direction, the woman performs 0 joules of work. There is no work being done. Why? Because the vertical direction in this scenario is perpendicular to the direction of the displacement, not parallel. It has to be parallel. It has to be in the same plane, along the same axis, okay? So now let's calculate how much work does she do along that horizontal axis. So now we're going to say that our displacement is here along the x-axis, and that is going to be a value of 5 meters. She moves the crate 5 meters horizontally. And now we are going to be using this component of her force, because that is the component that's in the same direction or parallel or along the same axis as the displacement of the object. So when we're getting ready to put our numbers into our formula, here's how this should look. Work is force times the cosine of theta, because it's at an angle, multiplied by my displacement. So once again, my force value is 100 newtons, but when I say times the cosine of theta, that's where I break it down into its individual component. Now, for this image, they didn't give us an angle for our theta, so let's just say that our theta here is 25 degrees. Sure, just make up a number here. So 25 degrees would go here, because it must represent the angle between the direction of the displacement and the direction of the force applied, which those are your two vectors there, okay? So that angle ends up being 25 degrees, and then we multiply that by 5. So if the woman applies 100 newtons of force at an angle of 25 degrees, then once we consider the horizontal component, she performs roughly 453 joules of work. And you see she is doing work, but if we compare it to our first example where all the force was horizontal, she definitely does less work, because it's simply a component that is being applied to create that work. Okay, so positive versus negative work. I just want to remind you that forces that are acting in the opposite direction, conceptually, we probably understand that that's going to be a negative force because it is opposing the direction of the object's motion. So our work is going to be negative work because the force opposes the direction of the motion. So you may fully understand that conceptually, maybe having an illustration where you can see that the direction of the displacement and the direction of the force are measured so that we have an angle theta. This angle is 180 degrees. Maybe I'll write that a little darker for you. This angle is 180 degrees. So when we apply that to our formula, work is equal to force times the cosine of theta times the displacement. Let's just stick with the same numbers so that we can see how it works here. Let's say that our baseball player has a displacement of 5 meters and the force acting on him is 100 newtons, okay? 100 times the cosine of 180 times our displacement of 5. The cosine of 180 is -1. So when I multiply all of this together, I am seeing that work is being done on the ball player, but what I'm seeing is that it's a negative amount of work because it opposes his motion, because the force is in the opposite direction. Now, this is why I've been saying that it has to be a force that is along the same axis or in the same plane, because in this case, the force is not in the same direction, meaning like they're both forward, but it's along the same planar axis, so therefore it can still be calculated in. When I simply put my angle in of 180, the calculator does the thinking for me and it tells me it's a negative value, okay? So this is what we need you to understand when we say that it is the angle between the displacement and the force. And you will need to think about that in order to interpret some of the practice questions that you will be seeing. All right, so now we're just going to work through a few examples. I'm going to go through these rather quickly. Let's start off with, I'm going to go ahead and write our formula down for us. I'm going to choose to continue to say F cosine theta. The formula on your formula sheet says FD cosine theta. It really doesn't make a difference mathematically which version of the formula you use. I just think that seeing that it's our force component that we're inputting kind of visually is what we're analyzing here, and so it makes more sense to me to regroup it like that for this conversation. But either way is fully acceptable and you'll get full credit, okay? All right, so let's look at this first example. If I have a force being applied here, and we're going to just continue this with our 100 newtons force and our 5 meters displacement. And I know we've already done this one, but we're just going to go through it real quickly so that we have everything on the same page. My force is being applied along the horizontal axis. My displacement is along the horizontal axis. So when I plug in my numbers, this is 100 times the cosine of 0, because that's what the angle would be between those two vectors, times 5. And so in this case, we would have a value of 500 joules of work that act on this crate. If we were to now look at this image over here on the right, we say here that we have still have a force of 100 newtons. We still have a displacement of 5 meters. But now when we consider the axis of the displacement and the direction of the force, those two are now going to be at a 45-degree angle. So when we go to plug in our numbers, it's 100 times the cosine of 45 times 5. So when we put that into our calculator, and let's just take a second and let's look at the cosine of 45 all by itself. If you put this into your calculator, you end up with some positive number. So I would like for you to see conceptually that we are going to have a positive value for the work performed here, either because you can see that the component of the force is in the same direction as the displacement. So if we were to look at what F cosine theta means, that's going to represent this force component right here, which would be in the same plane. So the force is not only in the same plane, but it's also in the same direction, pointing to the right for this particular example. So we would have a positive force applied, so we would have positive work done. When I look at the value of cosine of 45, it is a positive value. When I plug these numbers into my calculator, I get a positive value, okay? So it's positive work being done, specifically because the force applied is in the same direction, in this case to the right, as my object's displacement. Okay, so let's look at this picture over here in the bottom left. We're going to bounce around a little bit. Let's look at this image. So here I have a force of 100 newtons that is now being applied perfectly straight up. My displacement of 5 meters is to the right. So this angle here is my angle of 90 degrees. So 100 times the cosine of 90 times 5, and we've already done this. The cosine of 90 is 0. So this comes out to be 0 joules of work. If we look at this image here, I have a force of 100 newtons that's being applied. The box is still experiencing a displacement of 5 meters. So this would be a situation perhaps in real life where we have an object that's already in motion to the right and we're trying to bring it to a stop. We are pulling on it, we are slowing it down, perhaps we are eventually bringing it to a complete stop. So conceptually, I hope you can see that this is going to be negative work. Our force is being applied at an angle so that the horizontal component here is actually in the opposite direction of the direction of the object's motion. So it's a negative force applied here in terms of that directional aspect. This is going to give us negative work. Let's look at how the math is going to provide that negative value for us. In this particular example, my axis for the direction of the displacement is horizontal, but here is my force vector. So this angle is 135 degrees. So if you were to grab your calculator and type in cosine of 135, it's going to spit out a negative number for you. So when we calculate this, we're going to calculate a negative value. Just so happens it's negative 353. And so that's going to give us negative work done. The last example that I have for you is 100 newtons of force, 5 meters of the displacement. Our angle is from here to here. So 100 times the cosine of 180 times 5. And again, we've already talked about how the cosine of 180 degrees is equal to a negative 1. And so this is also going to spit out a negative number for you. And this, let's move this guy over. This is going to give us a value, of a negative 500 because all of the force, 100 newtons, is being used, so the magnitude is going to be the same for picture A as it is for picture E because they're both 100 newtons of force. It's both a displacement of 5 meters, but because it's in the negative direction or the angle is 180 degrees, it comes out to be a negative value. But all of the force is being used to perform work. It's just negative work. All right, the last thing that we need to discuss is power. So we have already talked about how power is work divided by time. And so remember, this is work in joules, time in seconds. If it's not in seconds, yes, you have to convert it. And then power is going to be measured in watts. It says here that power is also needed in order to accelerate an object. So we're now talking about changing the velocity. So let's talk for a second about what velocity is. Velocity is distance or displacement divided by time. So if we have power, which is work divided by time, and we don't know what that work value is, then we can expand that and we can say that is force times displacement divided by time. So if I just take a second and look right here, there's my distance over time. That is velocity. So what we want you to know now is you can also calculate power by multiplying force times velocity. So you now have a second formula for calculating the power, assuming that you know the force and the velocity.